All right, so let's talk about force diagrams and forces with no friction involved. So let's say that I have this block sitting on a surface. What forces do I have here? Well, I have my force due to gravity, right, the weight of the object pointing down, and I have this normal force pointing upward. So using this diagram, I need to create a set of equations. Remember that Newton's second law, force is equal to mass times acceleration, and because these are vectors, I'm going to have a summation of forces in the x direction, and I'm going to have a summation of forces in the y direction. So the easiest to start with would be the summation of forces in the x direction. There are none. Fantastic, great work. So what about a summation of forces in the y direction? Well, my summation of forces in the y direction is mass times acceleration. What forces do I have in the y direction? Well, I have my normal force and I have my force due to gravity and mass times acceleration. So the next thing I want to do is I want to incorporate directionality here. And when I incorporate directionality, I'm going to lose my vector sign. So my normal force is in the positive direction, so it's just going to be a positive value. My force due to gravity is in the negative direction, so negative Fg. Now that I have incorporated directionality in this equation, I have magnitudes of these vectors. I already pulled the directionality out. The directionality is already incorporated into my equation. So if I have this object that's just sitting on a surface, right, I have no acceleration, right? This is an example of static equilibrium, so it's going to be equal to 0. So I know that the force due to gravity is equal to negative mg, but I already pulled out my negative sign. So what I need is I need the magnitude of this force, meaning that my Fg is mg. So I can go ahead and put that my normal force minus mg is equal to 0. And in this situation, I see that my normal force is just equal to the mass times 9.81. Right? This is a fairly straightforward example. This is probably the easiest example that there is. Now, what if we make this a little bit more complex, right? We add an applied force that is coming off at an angle. Well, I still need to draw all of my forces on here. So I have the force due to gravity, and I also have a normal force because this object is sitting on a surface. Now, the problem is that my applied force is not fully in the x direction or fully in the y direction. Remember that because I have a summation of forces in the x direction and I have a summation of forces in the y direction, I need to incorporate this applied force into either an x direction or a y direction. So I'm going to draw a coordinate system, x, y, and my applied force is coming off at an angle, meaning that I need to find the x component of this force and I need to find the y component of this force, just like we did with kinematics. So this is just going to be a right triangle, right? If I have the force applied, I am going to have the x component of this force and the y component of this force. So once I have these, I can start to create my summation of forces. So what forces do I have in the x direction? Well, I have, let's put mass times acceleration. I only have one force in the x direction, and that is the x component of this applied force is equal to mass times acceleration. Now in this setup, because I have no friction, I have a frictionless surface, this object would have some motion in the x direction. So the next thing that I can do is I can break this force applied to the x direction into a more specific version, right? Because this is the cosine, this would be the force applied cosine of theta is equal to mass times acceleration in the x direction. So what about the y direction, right? The y direction is actually a little bit tricky because it requires some thinking here. So easy part is my summation of forces, right? I have my normal force, I have my force applied in the y direction, and I have my force due to gravity. Now, is this object in this current situation accelerating? No, it's not. How do I know that? I know that because there is a normal force, right? If this object is accelerating in the y direction, it is going to lift up off of the table. If it's lifted up off of the table, I can't have a normal force. So in this specific snapshot, there is no acceleration in the y direction. I think it's important to remember that just like with kinematics, we had snapshots in time. Whenever we're doing these forces and we're solving these force problems, we are looking at snapshots in time, right? We are looking at one specific situation. Like I took a picture and I am drawing all the forces that are occurring in that situation in the picture, right? So in this picture, because I have a normal force, I cannot have acceleration in the y direction. If I have acceleration in the y direction, my object would not be touching the table. So the next thing that I can do is I can incorporate directionality. I like to do directionality next and turn everything into magnitudes. This helps me make sure that I do not have a directionality issue in my algebra. So my normal force is in the positive direction. My force applied in the y direction is also going to be in the positive direction, but my force due to gravity is in the negative direction. Now I can replace the FAY and the force due to gravity with the magnitude of this applied force sine theta. It's sine theta because it is opposite, and negative mg, and this is equal to 0. So this is a great example of when my normal force is not going to be equal to the force due to gravity. Even though they oppose each other, because I have this applied force, there is going to be a little bit of the weight of the object that is taken into that applied force, right? So if this is rope, some of that rope is going to be holding the weight of the object. Not all of it is going to be sitting on the table. So I can solve this for my normal force, and this is going to be mg minus the magnitude of the applied force sine of theta, right? So in this situation, my normal force is not going to be equal in magnitude and opposite in direction to the force of gravity. So what about a block on an inclined plane, right? Assuming we still do not have friction, what is going to be happening here? Well, I think for this setup, it's important to think about what would happen if I have a slab of ice and I put a block on this slab of ice and it's at an angle. Well, I know, number one, this object is going to be moving down this inclined plane, right? There's nothing to resist the motion of this object, the pull of gravity downwards. So there has to be some sort of acceleration. So the next thing we need to think about is our coordinate system, right? And I like to rotate the coordinate system so that the x is along the surface of the inclined plane and the y is perpendicular to the inclined plane. I think that this simplifies the problem. There are other ways to do this. This is the most basic and simple way, right? So we're used to thinking about a coordinate system, x, y, straight horizontal, straight vertical. All I did was I just rotated this so that the x direction is along the surface of the inclined plane. And this is going to simplify our summation of forces. So I'm just going to redraw this down here, x, y. So my force of gravity is going to be pointing straight down towards the earth. Now my force of gravity, right, is not fully in an x direction, it's not fully in the y direction, it's coming off at an angle. I also have a normal force here, right? There is an object sitting on a surface. This normal force is going to be perpendicular to the surface of the object. Now, because my force of gravity is coming off at an angle, I need to break it into the x and y components. So when I do that, right, my x is now along the surface of this inclined plane. So my x component is pointing down the inclined plane, and my y component has to be 90 degrees from that, is going to be opposite of this normal force. So this is still just going to be a right triangle, but now my angle is going to be found here. So how are we going to find whether or not this is like sine, cosine, etc. Right? So I can take this, right? This is still my theta, and rotate this, right? So my theta is now here. And I can transition the x component over, and we can see that this is still just a right triangle. So I have the magnitude of the force of gravity, my theta is the angle, but now the y component is going to be cosine and the x component is going to be sine, right? So SOHCAHTOA, sine is going to be opposite over hypotenuse, right? So my sine is going to be the x and my cosine is going to be y. This is a great example of why we do not want to always assume that x is cosine and y is sine, because sometimes it is flipped. Each situation, we really should stop, take a minute, think about it, take our time when solving these problems. Honestly, to do anything well in life, we have to take our time. We have to, not rush through things. This will train you in patience. So now I need to create my summation of forces. So I have a summation of forces in the x direction is equal to mass times acceleration in the x direction. Well, I only have one force in the x direction, right? It is the force of gravity in the x direction. And I know because there is no other force acting in the x direction, that this object is going to have to be sliding down this inclined plane. I know that this is going to be moving in my positive x direction, so this is just going to be FGX equals MAX, and I can replace FG with the magnitude of the force of gravity. This is now going to be, right, sine theta is equal to MAX, and my FG is equal to mg sine theta is equal to max. Oh, look, my acceleration in the x direction is just g sine theta. My mass doesn't matter. What about in the y direction? Well, my summation of forces in the y direction is equal to mass times acceleration in the y direction. I have two forces in the y direction. I have my normal force and I have my force of gravity in the y direction. But this has to be in equilibrium, right? If we think about an actual physical block on an inclined plane, this block is not going to levitate up off of the inclined plane. It is not going to sink back down into the inclined plane. So there is no acceleration in the y direction. Now I can incorporate directionality. The normal force is going in this positive y direction, and my force of gravity in the y direction is going to be negative, right? It's going in my negative y direction. It's pointing down. This is going to be equal to 0. I can now replace FGY with my normal force minus the magnitude of the force of gravity, cosine theta. This is equal to 0. And the magnitude of my force of gravity is mg. So will be cosine theta is equal to 0. So now my normal force is equal to mg cosine theta. And this makes sense, right? Because my normal force is equal in magnitude and opposite in direction to the y component of the force of gravity.